thermodynamics in general, and in particular about ab initio thermodynamics and how we can use it to model materials. So why do we need to do this? Why do we need to bother about thermodynamics? A material is usually a collection of a large number of particles. And at finite temperature, there are many processes that are going on. And eventually, this collection of particles will tend to an equilibrium. And this is what thermodynamics is about. It describes the state of material in equilibrium and also how the material goes to this equilibrium. The thermodynamics determines defect, in particular defect concentrations and phase transformations, but it also influences magnetic properties, surface reactions, and crystal growth, although the latter two are controlled by kinetics, and you will hear more details about this in the next lecture. So another important point is that if we have a material, there is always a particle exchange between this material and the surrounding atmosphere. So if we consider, for example, a metal surface in an oxygen atmosphere, and so atmosphere characterized by a certain temperature and pressure, then we can calculate the number of times that molecules hit a particular site at the surface per second. And for temperature, for the room temperature, 300 Kelvin, and the pressure of 1 atmosphere of oxygen, we get that each site at the surface is hit 100 million times per second. So this means that if there is a tendency for the molecule to adsorb at the site, even if there is a barrier, eventually it will happen, and the surface can change its composition. So this adsorption will take place until the equilibrium is reached, and it is required to have very low pressure to actually keep a clean surface actually clean. But if we have very low pressure, then eventually, if we have, for example, an oxide, the oxygen starts to outgas from the material, and this will change, of course, its properties, in particular catalytic properties. So this point in equilibrium, which is reached during this process, depends on temperature, pressure, volume, and some other parameters, which I will mention later. So the point in equilibrium, for example, for this case would be whether we have a surface oxide, if we have some defects in the material, or we have complete oxidation of the bulk. So the equilibrium in thermodynamics is characterized by thermodynamic potentials. And here I list the most important ones, but there are more potentials. So the first one is internal energy. This is the one that contains the electronic energy and also the vibrational energy. Then we have enthalpy, which is the internal energy plus pressure times volume. Helmholtz free energy, where we subtract from the internal energy the temperature times entropy, and the Gibbs free energy, which is Helmholtz free energy plus the pressure times volume. There is a energy balance equation or energy conservation law, which states that a change in the internal energy should be equal to the amount of heat that we give to the system or remove from the system, the work that is done on the system by external pressure, and also the change in the number so the change in energy due to the change in the number of particles in the system. And this term, this coefficients mu I are called chemical potentials. So they show how these thermodynamic potentials are changing under particular conditions. For example, how the internal energy changes when we change the number of particles by one of given type, if the entropy is constant and volume is constant, or how the Gibbs free energy changes when we change the number of particles if temperature and pressure are constant. So why these potentials are important? Because at constant temperature, the system minimizes not the internal energy, which we minimize, for example, when we do the electronic structure, the atomic relaxation in our calculations, but it minimizes the free energy. If also the volume is constant, then the energy that is minimized is the Helmholtz free energy. But if temperature and pressure are constant, which are typical conditions when we study, for example, surfaces or in some gas atmosphere, then the energy that is minimized is the Gibbs free energy, which is also expressed as the sum of chemical potentials times the number of the given species. So this is all fine. We have these thermodynamic potentials that characterize the system as a whole, but how do we connect this information? How do we calculate these potentials from the microscopic theory? This is possible. So internal energy we know how to calculate, but what about the entropy? And the entropy we can calculate like this, where K is a constant and log is an old notation for the natural logarithm of the so-called number of microstates. I will explain a little bit more later what do I mean by microstates. So number of microstates for a given macrostate. So this is the basics of thermodynamics. And here you can see, so this expression was carved into the gravestone of Ludwig Boltzmann. And actually, in this form, this expression was suggested by Max Planck, but he insisted that this should be carved on the gravestone of Boltzmann. This is actually only a postulate, but it works, and that's the important thing, of course. There are a couple of reasons why it should work. First of all, in equilibrium, the number, so we know that the entropy tends to increase. It goes to maximize. And in equilibrium, so also the number of microstates are maximized. So this is correct for this function. And another important thing is that while entropy is additive quantity, the number of microstates is a multiplicative quantity. And this, again, there is a correct relation between the entropy and the number of microstates if it's expressed like this through the logarithm. So let's consider a system that can be in one. So we have a material, let's say, we have a huge number of particles, and the system can have a huge number of states. And let's consider this system which can be in one of the states with energy EI. Then at a given temperature, the probability of the system to be in state I would be expressed like this, where this is the Boltzmann exponent, e to the power of energy divided by kT, divided by a normalization constant, so that the sum of all probabilities of the system to be in each state is equal to 1. This is expressed like this. The Z has its own name because it's very important. It's a partition function. Now, we want to understand, so if we have a system, it evolves somehow in time, tends to equilibrium or is in equilibrium. So we want to describe this. And in order to do this, we can use ergodic hypothesis. It's another important hypothesis in thermodynamics, which states that the average over time is equal to the average over ensemble. This hypothesis holds if all states, all the microstates in the system are equiprobable, which is true for most realistic systems. Only some idealized system may break this rule, this theorem, but for most realistic systems it's true. So So we can use this hypothesis to find out what are the values of entropy and thermodynamic quantities and thermodynamic potentials for our system. What we do is we consider an ensemble of n replicas of our system. So we make an ensemble, and we should count the number of microstates of this ensemble. So the number of microstates, a macrostate describes which replica is in which state, while the macrostate describes how many replicas are in given state. So this is the difference. And now we can calculate the number of microstates. So if we have n replicas, and let's say that n1 of these replicas are in state 1, then we can calculate the number of microstates, number of ways we can distribute replicas among the state, so on state 1. This is given by this combinatorial, the binomial coefficient, right? Then for each of these states, we have the remaining particles, n minus n1. They can be in state 2, and so on. And if I combine this expression, I will get this kind of expression for the number of microstates. So the probability, so the number of replicas in state I would be given by the total number of replicas multiplied by the probability to find a system in state I, which is given like by this expression. And then we can calculate the entropy for this system of all replicas, which is expressed like this. So it's k logarithm of this number of microstates. Now we can use the Stirling formula, which expresses the logarithm of factorial of a number in this way. So, and after we do this, and after we substitute instead of ni these expressions, we obtain the expression for the entropy of this system of replicas. Now, the internal energy by definition is this kind of expression. So it's the sum of over states, energy of the states times the probability to be in this state, and times the number of replicas that we have. So now we can calculate the average quantities per replica, right, of our potentials, thermodynamic potentials. So for the internal energy, we have this expression, kT squared, derivative of logarithm of z over t, and so on. So we can express all quantities through the partition function. That's why it's so important. The most simple expression is for the Helmholtz free energy, which is just minus kT times logarithm of the partition function. Now, from these expressions, we can actually calculate the chemical potential now. And this is just done by taking the derivative of the free energy with respect to number of particles in the system, which is this expression. So let's consider a particular example of a metal surface in the oxygen atmosphere in equilibrium with the oxygen atmosphere. So the change in the Gibbs free energy upon absorption of oxygen atom on the surface can be expressed like this. So this is the Gibbs free energy of the surface with the additional atom minus the Gibbs free energy, the initial Gibbs free energy, plus the chemical potential of oxygen in the gas, of oxygen atom in the gas phase. I forgot to mention an important thing. In equilibrium, the chemical potential is the same everywhere. So in the gas phase, or at the surface, or in the bulk. So what we want to do, we want to find a surface composition and structure that minimizes the Gibbs free energy, right? Because the Gibbs free energy is the one that is minimized at constant temperature and pressure. So I can write, let's introduce a surface free energy, which is written here. So so here I consider a reference state, which actually is completely arbitrary. If we start from a clean metal surface, then this clean metal surface can be a reference state, where the NO_ref is the number of oxygen atoms in that state, which in the clean metal surface would be 0 here, and this would be 0. And so this quantity, yes, and there is a, we calculate the surface free energy per unit area. And so the structure and composition that the surface will have at given temperature and pressure will be the one that minimizes this surface free energy. So as you can see, this surface free energy depends on the chemical potential. We have to know the chemical potential of oxygen atom. So how can we calculate it? As I mentioned before, the chemical potential is the same in the equilibrium, is the same in the gas phase or at the surface. And therefore, we can calculate it for the gas phase. So let's consider a gas of n non-interacting diatomic molecules for simplicity. We can, of course, consider many atomic molecules. So each molecule has the following degrees of freedom: nuclear, electronic, translational, rotational, and vibrational. And we can correspondingly write the partition function in this way. So it's a product of the partition function for each molecule to the power of n, right, where n is the number of molecules. The translational degrees of freedom are special, and therefore there is this additional factor n factorial by which we should divide this z n translational to the power of n. Because the translational states, so they are represented by delocalized wave functions, they are invariant with respect to any permutations of molecules. So this is very important point, because so only because of this we get the closed relations that depend only on temperature and pressure, as you see further for the chemical potential. So so now we can use this formula to calculate the chemical potential. So it's a derivative with respect to n, and we obtain this expression for the chemical potential. So let's consider the translational degrees of freedom first. So this is a translational partition function, and this n comes from that normalization factor. Now, if we use the ideal gas law, we obtain for this part this expression. So if we didn't have this normalization, then actually we would get a dependence on the, so we will not get only the temperature and pressure here in this expression. So this was very important. And in order to calculate this, we only need to know the mass of the molecule. The electronic degrees of freedom, so the partition function for the electronic degrees of freedom is calculated like this, where 2si plus 1 is the degeneracy of an electronic state I due to spin. So usually this, the ground state, the separation between ground state and the excited state of a molecule is much higher than the thermal energy, the kT. And in that case, we can keep only one term here, which would be this part, so only the ground state energy. As you understand, this is not always true. Right? In principle, there are molecules which have degenerate states. Then we have to take into account this presence of degenerate or quasi-degenerate electronic states in the molecule. But in oxygen molecule, at not very high temperatures, we do not have this problem, so we can keep this only the first term. And the corresponding contribution to the chemical potential is given by this formula. What we need to know is the energy of the electronic state and the spin of the molecule. So the rotational degrees of freedom are expressed in this way. And here again, we have an important factor. So we sum over the rotational quantum numbers. But we have also this factor, which is equal to 2 for homonuclear molecules and 1 for heteronuclear molecules. So it's similar to that case of the translational degrees of freedom, where the state was not distinguished if we permute the molecules, and here it's the same. So if we permute 2 nuclei in the molecule, in the homonuclear molecule, nothing changes. So we have to have this factor. And finally, in order to calculate the rotational partition function and rotational contribution to the chemical potential, we need to know the rotational constant of the molecule, which we can either calculate, or there are very accurate measurements of the rotational constants for molecules from microwave spectroscopy. So in order to calculate the vibrational contribution to the chemical potential, we write the partition function for the vibrational degrees of freedom. And if you go through this formulation, you will see that the sum, so here the product is over different modes of a molecule, different vibrational modes, while the sum is over the states, right, for each mode. And we can rewrite it a little bit, and we will see that this is actually a geometric series, and we can sum this up and obtain this kind of expression. So for a diatomic molecule, the resulting contribution to the chemical potential is given by this expression. And what we need to know to calculate it is the vibrational frequency of the molecule. In most practical cases, we can neglect the interaction between the nuclei, the nuclear spins, because it's very weak. But of course, at very low temperature, it becomes very important. So now we can calculate, using all these formulas, we can now calculate the chemical potential of oxygen molecule and correspondingly of the atom. And here I show the results. So the different contributions are shown by different color. This is the chemical potential as a function of temperature. It is always convenient to define a reference for the chemical potential. This, again, doesn't change anything in the final results, but the numbers that appear here become convenient. For example, if I just use a total if I use total chemical potential of oxygen molecule calculated with PBE, I would have about 4,000 EV numbers here, right? So we just use a reference here, which is the total energy of an oxygen molecule. So this is why it's called delta mu. As a function of temperature, so we have the different contributions, the vibrational, then we add rotational, and finally the translational contribution. For oxygen, because it has spin, there is also the electronic one. The electronic contribution is non-zero. But for CO molecule, the electronic contribution is 0 because it has no spin in the ground state. So, and this crosses, the X shows the experimental values. So we can see that this delta mu is actually quite accurately can be calculated even with PBE. Alternatively, we could use this expression where the delta mu at given temperature and pressure is expressed as delta mu as a function of temperature at given pressure plus KT logarithm pressure divided by some reference pressure, which is usually the atmospheric pressure, and get these quantities from thermochemical tables from some reference data. So, now we proceed to calculate the free energy of the surface. and find out which one is stable at given temperature and pressure. So again, this is the formula for calculation. We calculate this change in the total energy, in the total electronic energy from our code between the current state of the surface and the reference. Then we can also calculate the vibrational contributions so the vibrational Helmholtz free energy. But there are other contributions which I will talk about a bit more. The configurational entropy, for now we neglect. And usually this pressure times volume term can be also neglected at realistic pressures. And the chemical potential we now know how to obtain. The vibrational contributions to the free energy are calculated like this. And so in principle, what enters here in this part here is the difference between vibrations of a current state of the system and the reference system. And because of this difference, this contribution actually often is small, but not always, and I will show an example when it's important. This f of t omega function is a phonon density, a function that we obtained before, right? And we have to use, and this sigma is the phonon density of states. So, so again, we consider the metal. In this case, as an example, we consider a palladium metal in the atmosphere of oxygen gas above it. So the reservoir for oxygen atoms is this gas of molecules, right? The oxygen gas at given temperature and pressure. The reference system is the bare metal surface, and the half of oxygen molecule is the reference for the chemical potential. So that the total chemical potential is just the delta mu O plus this, the reference value. Now, for now, we neglect the vibrational contribution and also configurational entropy. With this approximation, we can write the surface free energy like this. So it's the energy of our slab with a certain number of oxygen atoms at the surface in a certain configuration, minus the energy of the bare metal surface, minus number of atoms times the half of energy of oxygen molecule, and this term where this is the number of oxygen atoms times the chemical potential. So, this free energy of the surface is a linear function of this chemical potential, and we can just plot this linear function for each surface configuration. So the strategy is that we calculate different phases of adsorbed oxygen at the surface, right, or surface oxide, and then calculate the free energy as a function of chemical potential, which can be converted to the function of temperature and pressure through the expressions that I showed before. So here on this plot, you see this difference between the surface free energy and the reference free energy of the surface, of the clean surface, as a function of chemical potential of oxygen, and here it's converted to the temperature and pressure. So for two different temperatures, we have different pressure scales. So we see, so this horizontal line at 0 corresponds to the clean surface, right? Then, and then for different structures of adsorbed oxygen, we get different lines that describe the free energy of the surface at a particular condition. And so from this example, we already can see the power of the method and how intuitive results it gives. So we can see that at very low oxygen chemical potentials, which correspond to extremely low pressures, but it also depends on temperature, right? At higher temperatures, you do not need so low pressures to reach these conditions. So we have a clean surface that is thermodynamically stable. But then as we increase the pressure of oxygen or decrease the temperature, another surface state becomes thermodynamically stable, which corresponds to this P2 adsorbed oxygen at the palladium surface. And finally, as we continue to increase the oxygen chemical potential, we obtain, at some point, we obtain another state which is thermodynamically stable, which corresponds to the formation of surface oxide. If we continue to increase the oxygen pressure, at some point the bulk oxide becomes thermodynamically stable. So this gives us the kind of knowledge about the conditions, temperature and pressure, at which we expect the oxidation of the surface and then maybe formation of the bulk oxide. But the point is that it looks here that these transitions are very sharp, right? At some point I have a clean surface, then suddenly I have this one. This is, of course, in reality not the case, because we calculated a finite number of configurations, right? So here we calculated several configurations of adsorbed oxygen, but in reality there may be many configurations with closed energy, and therefore this and the configurational entropy will also play a role, and therefore these transitions will become smooth as they are in reality. But nevertheless, this allows us to get a picture and estimate of the conditions at which these changes to the surface occur. So if we consider a mixture of oxygen and CO gas, then actually a thermodynamic equilibrium of this system would be oxygen and CO2, because CO2 is more stable molecules than CO. However, this reaction the barrier is very high, and this reaction is very slow. And in reality, it makes sense to consider a so-called constrained thermodynamic equilibrium. In this constrained equilibrium, we assume equilibrium between each of the species, oxygen and CO, and the surface, but no equilibrium between them. And now our goal is to figure out at which conditions temperature and pressure and partial pressures of oxygen and CO2, what kind of stoichiometry does the surface have. And for this, we again calculate the surface free energy. Here should be also partial pressure of CO. Sorry, I made a mistake. And here again, we have the difference between total energies of the system with adsorbed oxygen and CO and the reference system. And now we have contributions from chemical potentials of both oxygen and CO. So mathematically, this equation corresponds to an equation of a plane, right? Instead of lines, we now have the planes. So if we plot these planes, for each calculated configuration of the surface, we obtain such a plane. So this is the free energy, and these are chemical potentials of oxygen and CO. And what we do, we try to figure out which surface is the most stable. We just look from the bottom of this thing, and that's what we get. We get conditions at which one or another surface stoichiometry is thermodynamically stable. In this example, we consider CO oxidation on ruthenium oxide 110 surface. Here is the picture. Ruthenium is shown in this light blue color and oxygen in red color. And we consider adsorption of oxygen and CO on this surface. There are two different sites for adsorption of this species, the bridge site and the Kuss site. And when we analyze these results, we obtain the following phase diagram. So the vertical axis shows the chemical potential of CO. The horizontal axis shows the chemical potential of oxygen. And the different colors show different stoichiometry of the surface. So what we find is that at very low chemical potentials of CO and oxygen, we have the bridge sites still occupied by oxygen, but the Cus sites are empty. So this is because the oxygen at the bridge sites is very stable. It's very hard to remove it. Then if we start to increase the oxygen pressure, we start to see the adsorption on the Cus sites, thermodynamically stable. And if we increase the chemical potential of CO, then this oxygen at the Cus sites is replaced by CO at the Cus sites. And finally, at very high chemical potentials of CO and low chemical potential of oxygen, we can have the whole surface covered with CO. So this gives us a picture of how the surface changes depending on the conditions and partial pressures of oxygen and CO, or on temperature. And it also gives us kind of a zero-order approximation to the possible activity of the surface. And here, this area shows where the surface is catalytically active for the conversion, for the oxidation of CO. And it's not a coincidence that this area is actually on the border between two different phases. So because at this border, the surface doesn't particularly know, doesn't know in which state it wants to be, right? The Cus sites can be occupied by oxygen and CO, and so there is no poisoning by either of the ingredients, and the reaction can go. And so this is kind of a first order picture of chemical activity of the surface. But the true catalytic activity should be described by kinetics, and this will be discussed in the next lecture. So far we neglected vibrations, but this is not always the correct strategy. Sometimes they are very important, and here I take this example from this paper of adsorption of water and oxygen on zinc oxide polar surfaces, polar surface 0001. So this is the phase diagram if we neglect the vibrations. This T equals 0 just means we neglect the vibrations. So this is the chemical potential of hydrogen, the vertical axis, and this is the horizontal one is the chemical potential of oxygen. So these conditions here, with stripes corresponds to liquid water, the condensation of liquid water at the surface. And here we have some surface phases, in particular this 2x1 OH, adsorbed OH, and this kind of reconstruction. Here we have a small area of this reconstruction, roots 3 by root 3 are 30° O and 2x1 H. And then we have a large area of conditions where we have the complex so-called triangular reconstructions here. So this is what we get from by assuming that there are no vibrations. However, there is no structure, if you look here, there is no structure with a 2x2 periodicity, which was actually observed experimentally at this zinc oxide surface in a dry oxygen atmosphere. So what's the problem? Is it our functional? It's actually not the functional, it's the vibrations that we neglected. The vibrations stabilize another phase, which is 2x2 adsorbed oxygen surface reconstruction. So this is shown here, and these are the experimental conditions at which this reconstruction was observed. So this is in very good agreement with these results. There is also the range of conditions at which this reconstruction is stable becomes larger, so it increases, and this is also consistent with experiment because this kind of reconstruction was observed at more humid conditions. So this means that vibrations are indeed important, and if you want to neglect them, you have to check or estimate their contribution first. Another important area where thermodynamics is very important is the thermodynamics of defects. So defects are very important because they can change the properties of material, of a base material significantly. Here is an example of magnesium oxide single crystals. Magnesium oxide has a large band gap, about 8 eV, and so single crystals should be transparent. And they are almost, but you see a bit of brownish color, right? This color comes from impurities of iron. And actually what you see by naked eye there is the ppm level of iron. So there is 1 part per million of iron, and you can see it with naked eye because it's so optically active. So in general, the very small concentrations of defects can significantly modify materials' properties. The very famous example is, of course, silicon semiconductors, where currently the intentional impurities per atom are 1 per billion, actually, which are used in electronics. Another example are pressure stones, of course. So this is all of these differently colored stones are the same material, the same base material. It's a sapphire, the aluminum oxide, but the different colors are given by different impurities. The red one by chromium, the violet by vanadium, the yellow by iron, the green one by iron at higher concentrations, and the blue one is by mixture of iron and titanium impurities. So the typical concentrations in this case are a bit larger, from 100 to 10,000 parts per million. So we can use thermodynamics to calculate the concentration of defects. How we can do this? So we can calculate the free energy of the system, and then we find out which concentration of defects minimizes this free energy. So in this case, so again, we have to calculate the entropy of the system, and there are different contributions, right? So there is a vibrational entropy due to phonons. There can be electronic entropy if there is a degeneracy at the Fermi level. But the system that we have is the solid with an atmosphere above the surface, right? And so there is also contributions to the entropy from the gas phase, which are vibrational, rotational, translational, etc., which is part of the chemical potential. And finally, we have this very important contribution for the defects, which is solid defect disorder. So I separated from the other contributions in a special part, which I call the configurational entropy. So this entropy is due to the fact that if I have a bunch of defects in my system, and these defects, assuming that these defects do not interact very much, so there are many configurations that are degenerate in energy, then I can calculate the number of microstates of this system, right? I can calculate by how many times, how many different ways I can distribute n small defects among n capital equivalent sites. And this gives me the configurational entropy. So this is the number of ways by which I can distribute these defects, and this is the entropy. Now we use the Stirling formula again, as I showed before, and we can write this configurational entropy in this form. So now what we do, we write the free energy for the system with the defects, which is just the free energy of the system without defects, some reference system, plus number of defects multiplied by the change in the free energy due to formation of a single defect. So this is called Gibbs free energy of defect formation, minus this T times configurational entropy. And with that expression here, we can actually differentiate it, right? And we can minimize this energy, just taking a derivative with respect to n and setting it to 0. And we obtain, from this we obtain the concentration. So the concentration here has this form, which actually maybe look familiar to you. This is a Fermi distribution. So Fermi-like distribution, like Fermi statistics. And it's clear why the defects actually should have this statistics, because there is exclusion principle. Each defect can, so each site cannot be occupied by more than one defect, right? So, but in case when this formation energy is much higher than the thermal energy, then we can neglect this one, and we obtain the Boltzmann, the usual textbook formula, which corresponds to this Boltzmann exponent. So exponent to the free energy of formation divided by kT. This is the relative concentration of defects to the number of sites. As I mentioned, we assumed that the interaction between the defects is such that most of the configuration of possible distribution of the defects between the sites are quasi-degenerate or degenerate. But this is not always the case, and one important example are charged defects. So if we have a charged particles, right, they interact, the interaction is very long range. It decays very slow. In fact, if we try to calculate a macroscopic system with a finite number of particles, okay, a finite number of defects, then the energy of such system will be very large. In fact, if we use a periodic model, we will get infinite energy. We must compensate the charge of the defect somehow. So the charge defects must be compensated in realistic materials. Otherwise, the energy is too high. I mentioned this before. So if you try to model a periodic system with a defect per unit cell, then you have to compensate. So in the bulk calculation, you usually just throw away the divergent terms, and this corresponds to introducing a uniform compensating background charge. And if you calculate the dependence of the formation energy on the unit cell size, you will find this typical dependence here. So this is the formation of a doubly charged oxygen vacancy in magnesium oxide, and this is what we get as a function of the 1 over lattice constant size. So we see that when we extrapolate to the dilute limit, the derivative does not go to 0. So there is always some strong dependence actually on concentration, even at very low concentrations. And this is, and if you look carefully also, you will see that the energy, the formation energy, reduces as we decrease the unit cell size. If we decrease the distance between the defects, which seems wrong, right? Because we have defects that are charged the same way, but the formation energy decreases as we decrease the distance between them. The repulsion should increase. But the point is that the dominating term here is interaction of defects with the compensating background charge. So this is attractive term. And if I increase the density of the defects, the density of compensating charges also increases. So so in real materials, if we want to create or we want to understand how many charge defects are there, we have to understand how these defects are compensated and how this compensating charge is distributed. In general, it's convenient to distinguish two different types of interaction between defects. One is the local interaction, which corresponds to change in the bonding when the two defects are close, or relaxation around this defect. And another one is this long-range contribution due to the Coulomb interaction between defects and between defects and compensating charge. So in this case, in the case of interacting defects, we cannot write this simple expression, right? So that we minimize so the minimization of the free energy does not lead us this very simple expression. We have to take into account the dependence of the formation energy on the concentration of defects. And this can be done in case of charge defects by including this interaction energy or the electric field energy due to the distribution of charges in the system as a separate part, as an additional part of the free energy of the system. Okay, I will skip this discussion. So what happens when we have a surface, right? And on this surface of magnesium oxide, in this particular example, and on this surface, the defects form. So in case of magnesium oxide, when we form an oxygen vacancy, there is a level in the gap which is occupied by 2 electrons, and this defect can be charged by removing these electrons. And if we have p-type doping in the magnesium oxide, then we have the states. The bulk Fermi level will be at this near the top of the valence band, and the electrons can jump from the defect to this states at the Fermi level. And that's how doping affects the formation energy of defects. So now we start to get a charge below the surface, which is distributed in the slab, a layer of charge, the space charge layer, so-called, and the defects that interact between each other and with this space charge layer. So this causes a so-called band bending at the surface, which just simply means built-in potential and electric field at the surface. And you can actually, for this kind of geometry, when we have a slab with some charge opposite density at the surface, we can calculate the electric field and going through the formulas. So apparently there is no time to do this. And actually using thermodynamics can calculate the concentration, so the concentration of the vacancies as a function of the concentration of dopants and also the space charge layer thickness. Okay, I can skip this. So in conclusion, we saw that ab initio atomistic thermodynamics approach allows to model materials in thermodynamic equilibrium at realistic temperatures and pressures. The surface phase diagrams and defect concentrations as a function of temperature and pressure are 2 important examples. And also, from the last examples with charge defects and doped material, we saw that the doping should be actually considered as a thermodynamic variable along with temperature and pressure, because it's as ubiquitous as they are. And thank you for your attention.